Okay, we're going to get started. Our first speaker today is Dipanjan Das, and he finished his bachelor's from IIT Kharagpur, India in 2013 and completed his MS with Professor Krein in 2016 and is currently working towards his PhD. His research interests are power electronics and control of power converters. He also likes photography and sometimes paints.
Right. Okay. Thank you, Cece. Uh, given a way. Okay. So my talk today is going to be on differential power processing for a CD stack of processors or processor cores, whichever one. They're both similar. So we have heard a lot of talks on differential power processing mainly from NVIDIA these days and from ETHA. So my work over here is it's slightly different from Enver's because he has been working on this on the server side, and my work is going to be on the processors or CD stacking of processors. So here's an outline of what my presentation is going to be today. So first, we are going to discuss why we are interested in stacking of processors or processor cores in CDs. What we do now is we just connect them in parallel, or we have several power converters on the processor IC which supply the processor core voltages, but mostly looks like a parallel power delivery. So designing a converter for a parallelly connected processor, or in which the cores are connected in parallel, is designing the converter on a PCB is very complicated. So here we have like a equivalent circuit of what a power supply on a PCB for a processor is going to look like. So first we have this is a buck converter stage. So first we have multiple phases of the buck converter, and then we have a bulk decoupling capacitor, which is usually electrolytic cap, and then we have some ceramic caps which are placed right next to the electrolytic caps. So this PCB impedance ZPCB1 is usually quite low, and after that we have some traces which connect it to the processor region, and we have some more decoupling ceramic capacitors right there, and here's where the processor is going to sit. So these are called cavity capacitors. So we have our second filtering stage over here, and then our power is going to be transferred from the PCB to the processor itself, and these are the sockets through which the power gets transferred. Now, the main problem with this power delivery method is that I need, for a processor, that voltage VTT that can be around 1 volt or 0.8 volt or 1.2 volt, that's very low, and they can sink a lot of current. Like some processors go even up to 200 amps, or maybe even like 300 amps for server processors. So our converter design has to be such that I have a very low effective impedance from here to here between in the power delivery path. So here's usually what the impedance of my output filtering stage looks like. So I have my bulk capacitor impedance over here, which is the red line, and then there's the magenta line, which is my ceramic capacitors over here, and then I have my third stage, which is the blue line, and overall effectively it should follow something like the minimum of these curves, or it's a bit more complicated than that, but I mean there's going to be a zero over here, and so that's what we see. The effective impedance is shown by the blue line, or yeah, the cyan line. And this low part of the impedance is actually significantly higher than what my capacitors provide. That's because of these socket impedances and PCB impedances. So if we want to lower the high frequency impedances at these points, then we have to use more copper on the board, and like we have to put parallel many more pins to have a low impedance power delivery. So what usually the processor pin map looks like is all the red pins over here are power pins, like more than on a 1055 or 1155 pin processor, I will have more than 300 dedicated pins to ground and to the power supply of the core. So for this, what Intel, like if we need even more power for future processors or even more current, then these pin counts which are dedicated to power delivery is going to increase drastically. So what Intel has been doing is they are integrating voltage regulators on their processor itself. So what we end up doing is we on the PCB we supply a higher voltage and a lower current. We design a power supply which delivers a higher voltage and a lower current, and they are internally converted to the core voltages on the chip itself. So if there are a few papers on fully integrated voltage regulators, which is what Intel is calling them, and the most recent paper on that says that they have integrated a 140 megahertz converter which has like 16 phases, and allowing switching at very high frequencies is also going to give you very high bandwidth. So the general trend that we want to follow is like we want to deliver power at a higher voltage and lower current. So this is what makes the FIVRs very useful. But we want to deliver power at an even higher voltage than 1.8 volts. So we connect processor cores in series, and what happens is that effectively the converter that is going to be designed on the PCB, this one, is having to supply like 8 times higher voltage than what was before, and it's also going to have to supply very 8 times lower currents. So my effective impedance of the buck converter that I'm going to need is going to be 64 times less for a series stack of 8 processors. But with series stacking, now I have to take care of the balancing between the consecutive core currents, and that has to be done with external converters as well. So this is This is where differential power processing comes in. So each of these DPP converters can be implemented as buck stages, or if you like, this can be considered buck boost or boost depending on how you're looking at it. But for control purposes, we can consider them as buck because the small signal model turns out to be exactly like the buck converter. And usually the core voltages are equalized, because it doesn't make sense if one processor is doing a lot of computation and another processor is doing low computation, and that is actually not an optimal way of sharing computation between different cores. So usually what the software does is balance the powers of each of the cores. And so and so we also similarly we also get that the operating voltages of each of the cores are going to be near each other. So using that, we see that the currents that the DPPs are going to have to process can be given by this. So the 7 DPP converters, if all the core currents are balanced, then they are going to provide like average of 0 current, and only one of the converters in this 8 converters in the total system is going to process the full power. So to get the most out of the differential power processing or CD stacking, we have to ensure that our DPP converters have very good light load performance, as in their light load power losses has to be very low. So how do we implement a good light load efficiency optimization control for our DPP converters, which look like this? So the synchronous buck stages that we had over here, they can be controlled by just complementary PWM, and if we do not allow the inductor currents to, or if we allow the inductor currents to change directions, then we can operate it in a bidirectional fashion. So improving CCM efficiency, if we are operating the DPP converters in 4 CCM mode, is quite difficult, as well as we are not going to get enough improvement out of it. This is how typically the efficiency curve is going to look for a CCM 4 CCM or 4 CCM DPP converter. So we are going to have like below 80% efficiency, below 1 amp for a converter that is made with a 4.7 microhenry inductor. So the general trend is like if we are increasing the size of or if we are using a higher value inductor, I'm going to have lesser core losses in the light load region, but I will also have more DCR losses in the high load region. So this is so we can see that from here that the red curve is with a higher inductor and the purple curve is with a lower value of inductance. But okay, so if we take like inductances with the same saturation current rating, and if we take a higher value inductor, then its size is also going to be larger. So do we have like a contention between, like, if I'm using a higher value of inductance, is my light load losses really going to be low? I mean, yeah, it's sure, because I can now operate it at a lower frequency, or if I want the same inductor current ripple, I can operate. If I want the same frequency, I can operate it at a lower inductor current ripple. So overall, the effect is that my light load losses are going to go low with a higher inductor. But how do we get more efficiency improvement? We have to use some kind of a discontinuous conduction mode for improving losses, or improving, like, reducing losses in this region. So usually some kind of a hysteretic controller is used for controlling the voltage or regulating voltage at light loads. For example, this is a voltage mode hysteretic controller, which generates the PWM pulses by comparing the inductor current over here, or V out plus the inductor current over here, and controls the top switch. And if this is a diode, like a normal buck converter, not a synchronous buck converter, then it will automatically go into DCM and automatically regulate the voltages. But we have a converter that needs to be bidirectional, and so we cannot have just a diode over here. We have to have a synchronous buck operating stage. So how do we reduce switching frequencies, or how do we reduce the switching while maintaining voltage balance for a bidirectional converter? So what we are going to do is we are going to have to estimate the load current, or rather the load current direction, And then, depending on what the load current direction is, I'm just going to operate this as a diode if the load current is positive, and if it is negative, then I'm going to operate this switch as a diode. But like, I mean, without current sensing, I have to use the body diode or a parallel diode. But that's what we have been doing. So, hey, Kevin. Okay, good. All right. So, estimating the load current is better than measuring the load current because measurements can have errors, and I cannot tolerate any error. If I have to have a proper zero current sensing of the load current over here. So what we do is we use current mode control, which generates an estimate of my of the load current of the load current that I'm going to need to balance the voltages. And so depending on the direction or the sign of that estimated load current, I'm just going to operate this switch or this switch as a diode. So these are some simulation results for like with this simple controller with a PI loop, with a PI controller over here. Now we see that the DCM operation is pretty regular till a particular limit. Below that, the frequency of my DCM inductor currents is going to be too low, and with the PI controller, the DC gain is going to be too high at those frequencies. So what my estimator is going to end up doing is that it will estimate that I need a negative current to balance the voltages over here. So it will send out a negative pulse, and then it will send out a positive pulse immediately after. And I don't want this operation because I should theoretically be operating, I should have no switching over here because my load current is very close to zero. So this operation will give me more losses. So how do we take care of this situation? Like, we need a lower DC gain for lightly loaded conditions so that this does not happen. So a simple solution is just to use a dead zone with the integral component, so that I reduce my integral gain when my output voltage is too low or my voltage error is too low. So with this dead zone generator, I can get what I want. That is, I have no switching when the load current is below a particular limit, and then again it starts regulating the voltages. So with this, we implemented this on hardware, and then we found that this is this demonstration of negative light load region to a positive CCM operation condition. So we can see that there's increased ripple in this region and CCM operation is in this region, and similarly we have the opposite, like a negative CCM to positive DCM transition, and it works fine, and we get some efficiency improvement in the light load region with this kind of control. But the problem is that we are not able to get a very significant amount of efficiency improvement in this region, and this is because my converter is already pretty inefficient in the light load region, where it enters where it enters DCM. My converter is only 77% efficient. It means that if I operate at that operating point, then even with DCM, I cannot have an efficiency value which is more than 77%. So how do we get better light load efficiency values? The solution, one particular solution, is to use multiphasing, so that we can use we use a lot of parallel converters. So each of these inductors can have a lower I saturation rating, so they are going to be smaller, and they are going to be much more efficient at light load. And also these switches are going to be designed for much lower current. So I'm going to have, for each single phase, I'm going to have many times lower switching losses. So I get a very good efficiency, which is I get very good efficiency values at low output currents. And then as my load current is going to increase, I'm going to multi-phase this, and I'm going to add more phases to the system. So eventually, for like a 16-phase system like Intel's FIVRs, I have a very flat efficiency curve around 90%. So yeah, we can build on this multi-phasing technique for light load efficiency improvement. But the thing is that with DPP, my converters are only going to process very low amounts of current for most of the time. So all my, maybe just I'm going to like end up eventually using these two phases for most of the time, and these phases are eventually going to be like off around most of the time. These phases are going to be off. So what do we do to, like, what can we do to reduce my board area that I'm going to spend on these 8 phases, which are almost always off? So we can group them together, like we can group 4 of the phases together and 2 of the phases together over here to get this asymmetric topology. And my plan is to control the inductor current of the high phase so that it always processes, it is always turned on when high current is needed, and most of the time these 2 phases are going to be operating. So the plan is to control it in this kind of fashion, where so I have a output current ramp, and my inductor currents are going to behave like this. So I can see that this inductor current is always around 4.5 or 5 amps. This the second or the third phase turns on only when 2 amps or 2.5 amps is needed from that, and the first 2 phases are only turned on when less than or around 1 amp is needed from them. So this way we can design the converters that have L by 4 inductance to be efficient near that particular operating point, near the 4.5 amp or 5 amp operating point. Then we can design this for similarly for the 2.5 and 1 amp operating points. So what kind of efficiency curve am I going to get from that? Okay, so without going into PFM, I can already see that my efficiency curve, I already have around 90% efficiency curve around the 500 milliamp, around the 500 milliamp region, which is much better than what we have gotten with a single phase 4.7 microhenry inductor. And with PFM, or with the light load control that we discussed before, I can get even more efficiency improvement in the light load region, up to 10 milliamps even. But this is only simulation results. I haven't been able to work on the hardware yet. So yeah, but it is promising that it will work out well. So what's the main takeaway point over here is that with PFM, I have much lower light load losses than just only operating at FCCM, and that is just going to go down as my power goes down, and it is going to converge to the control power over there. So how does this light load efficiency improvement affect my system level efficiencies? So first, so when my stack for this is these simulations are only done for a stack of 4 output or 4 core, yeah, of for a stack of 4 cores, and I'm assuming that the maximum current of each core is 10 amps. So with a variation, like we plot the system level efficiencies with percentage mismatch. So this is FCCM operation if my converters operated in FCCM and my stack current was an average of 10 amps. So we have a very high efficiency, and this is mostly because of DPP, because my converter is only going to process about 10% of the total stack power. So I have very high efficiencies over here, but it's going to be even more if I use the light load control. And then for lower value of stack current, which is like 10 times lower 1 amp, I see that my system level efficiencies are already going down below to around 96% from 99.6%. And this is because my converters are not that efficient for even more light loads. And also the stack current is low, so the P out is low, and the efficiency values are coming down with FCCM operation. But with PFM, I still have above 99% efficiency. And finally, the 0.1 amp stack current. My power output is now so low that my inductor or my DPP converter losses are really bringing the efficiency down if they keep operating in FCCM. But with light load control, I can still have around 93% efficiency. Okay, so yeah, the future work is first of all validating these asymmetric converter simulations through experimental work, and then setting up a realistic system of stack of processors with clock gate arrays. And yeah, we have to work more on what we are going to validate our system level efficiencies on. So questions? Yeah.
So if you go back to the slides, maybe, or 3 slides, I guess. So the blue line, is that, can you explain quickly, is that the system without your approach? Is that just like the basic architecture?
Yes, that's the basic architecture, only operating the DPP converters in FCCM.
So what about if you just looked at just a very standard architecture without DPP? What would the line be there?
It would probably be much lower than this, because usually we implement PFM in that region. So without PFM, if we are just going to compare that with something that doesn't use PFM at light loads, then it would be much lower than that, because my converters are probably 40% or 30% efficient at those efficiencies, or those operating points. Yeah.
So for DPP with servers, you can do like isolation converters, but for this is not.
Yes, this has to be non-isolated.
So is that okay for core to be
It
non-isolated?
so usually very high dynamic performance is needed for core voltage regulation. Like you can see from Intel's FIVR papers that they have like a 80 megahertz bandwidth, which enables load current tracking in the nanosecond region scale. So with isolated converters, it's going to be much more difficult to have such a good bandwidth maintained. Yeah.
For like communication purposes, I guess servers can be.
Oh, okay. So you mean okay.
Both are on the same chips and.
Well, for servers also you need isolation for communication, because if you stack servers, yeah. So
that's easier.
Yeah. Yes. So you can connect them with Ethernet or something like that, which already has isolation. But here, the only thing that you can do is you can use level shifters, which are not that fast right now yet, or you can use optical communication, which is also like 5-10 years from now.
Although TI is building a lot of new digital isolators now, because there are ground bounce issues in all these systems already anyway. So they're having to isolate the communication across these things. We take advantage of it.
Okay, let's thank our speaker again. Our next speaker is Desiree Phillips, and she is a fifth-year graduate student working with Professor Urbana. She received her BS in electrical engineering from RPI in 2012 and her MS from UIUC in 2014. Her research interests include computational techniques and the electric grid role in the water energy nexus.
Yeah, sorry. Should be the only one in there. All right, so my talk today will be impacts of water on the electric grid and how I propose to model them. So I'll just jump right into it. So water energy nexus, water for energy, and energy for water. So I'll be focusing on water for energy, in particular, hydropower and thermoelectric cooling. And so just to look at how much is used for thermoelectric cooling, this is a graphic I like to use. It was released by the Department of Energy in their 2011 report. And it shows that about 40% of all energy produced in the US is used for electric generation. But at the same time, about 50% of the water used in the US is used solely for thermoelectric cooling. And so the electric sector uses up a lot of this country's water on an annual basis. And so in the last 5-10 years, there have been a lot of water energy nexus groups that have been doing research. And so the key, I guess, conclusion that a lot of them reach is there's not enough cross-sector power system analysis. So there's water data, there's electric data, but there's not much being done to combine those two for cross-sector studies. And so my work will be looking at how I can incorporate water constraints and effects into electric grid planning and operation analysis. So the way I plan to do that is through game theory. So the electric grid has been moving towards deregulation. And so with that, there's been a shift from a vertical utility structure to a marketplace structure where there's bidding, and the participants, in particular the utilities, are creating competition environments. And so I'm using a game theory approach to model their competition. And so in game theory, the goal is to find the system's, what they call the Nash equilibria. And there can be more than one. But basically what this equilibria says is that given all the participants in a competition environment, their Nash equilibria would be such that all the participants choose a behavior or a strategy where they find no incentive to deviate from that strategy, given the strategies the other players are using. And so to measure that incentive, there'll be some sort of utility function which measures their payoff. And so you could think of, in the case of the electric grid, the payoff is simply the generation profits in the market. But I'll go a little bit more into how that works. Just to explain some of the terminology a little bit more, I'll go into a common two-player example that's used in game theory called the prisoner's dilemma. So you have two prisoners who are accused of a crime. The prosecutors don't have enough evidence to prosecute them with the highest charge. So there's the highest charge, which has a sentence of 10 years, and a lesser charge, which has a sentence of 1 year. And so then there's an intermediate. So the idea is each prisoner is isolated, and they can choose to, on their own, either confess to the murder or remain silent and not confess anything. And so these payoffs, what are called their payoffs, just represent their prison sentence. And so if you look at, for example, player 1, his payoffs are in orange, player 2's payoffs are in blue, and the strategies are to be silent or to confess. And so that's kind of the game theory terminology. And so in this case, if you go through, you'll find that the Nash equilibrium is actually for both of them to confess, which if you think about it, and this happens a lot when you study the Nash equilibria, what turns out to be the Nash equilibria isn't necessarily the best decision, because even if both remain silent, they would get a lesser sentence for each of them. But if you were to look at the Nash equilibrium from that position, neither one would want to deviate from their choice. And so how does this look in an electricity market? So they use what's called a pool co-model, which is basically they pool the generation and they pool the load. And they have a system where there's an ISO who oversees the submission of the bids from both the buyers and the sellers. So buyers will submit how much generation they can provide and what cost they're willing to trade it for, whereas sellers will request a certain amount of generation and then also submit a bid regarding how much they'll pay for it. And from there, the ISO does an OPF, determines, or an economic dispatch OPF, and determines what the market clearing price is. And from there, each generator can determine its profit based on the revenue from the generation sales. And so just to give an example of how you would manually calculate this, in this case, the product being sold is a bushel or a bushel of fruits in this case. So you have your sellers 1 and 2, and for the first bushel, they're willing to sell their first bushel at $10, $50, and then so on and so forth. For the 3 buyers, this is the price they'll pay for the first bushel, second, third, and fourth, if they're willing to buy that many. And then from there, you stack it. The supply curve is basically, if you organize each of these bushels by increasing selling price, you'll get the supply curve. If you organize the buyers by decreasing bids, you'll get the demand curve. And the point of interest, or in this case, the clearing price, will be the point at which this curve intersects. And that will be the price that the entire market sees. And so you can think of this section. So if you look at this point along the curve and you go down, then this area represents the seller's surplus, because they were willing to sell it for 10, but the market says they can sell it for 65. So you think of it that way, that these guys profited 55 for their bushels, so on and so forth. And so for generators have their cost curve, which is AI, which is the no load cost, plus BI, PI, which you could think of as the fuel cost coefficient for generator I, and then a CI, PI squared term. And so if you look at what it looks like for an incremental change in power from P0 to P, the delta CI comes out to this term right here. And it's just a function of the cost at the new point minus the cost at the old point. And so the incremental cost will just be the change in y over change in x. If you take the limit as delta p goes to infinity, you get the derivative, which is the marginal cost, which is just the derivative of the previous terms. CI will be the derivative of this guy. So it'll just be BI plus 2CI PI. So from there, how does the generator decide whether it wants to buy power from the market or sell power? Well, if it wants to get some profit and the market price is lower than the price or its cost to produce the power, then it's not going to create its own power because it's losing money because it'll sell it to the market at a negative profit. So if what's called the spot price is lower, generators will buy from the market. If the spot price is higher than their cost of production, then they'll sell it to the market for profit. And so the payoff is just that change in power versus the price of electricity plus TI, which in this case will just be the transaction. So how much power they're either selling or buying from the market. And so how does this buying, selling translate into participant strategies or utility strategies? So if we do straightforward economic dispatch, then you could just find that the payoffs are maximized when utilities trade at 2CI, and that M is just the slope of the cost, the marginal cost curve. But this is a bidding environment, so the market participants are not beholden to that 2CI, so they'll try to bid higher or lower to position themselves in such a way that they wind up becoming a participant in the market. Because in that previous situation, with the supply and demand curves, you could see that some of the bushels weren't sold in the market because they were too expensive. And so the same thing could happen with power. And so the strategies, just for this example case, you could bid higher than your marginal cost. So instead of 2, it's 2.3. Bid at your marginal cost and bid lower than your marginal cost. And this is just for an example case I'll go over. Just 3 utility example. So you have 3 utilities, each with 1 generator, and those are their price coefficients, and they each have a load attached to them. So if you run through the OPF, you'll get these marginal costs. And so this will be like the 0 point, the operating point beforehand. So now that maybe it's the next hour and they want to trade more power. So they decide to change their B coefficient such that they have changed their bids in the market. And so if they do that and I rerun the OPF, what will their new lambdas look like? That'll be their that will be what these, in this case, the payoff matrix is. So again, they could bid high. H is bidding higher than marginal cost. L is bidding lower. M is bidding at marginal cost. And these are just the payoffs. So if I wanted to show you the matrix, technically it would be 3-dimensional. So for this column, you could just think that A is bidding high and C is bidding high. And then this column is for B's bidding. So on and so forth. So the first term will be this total payoff for A and C, just for visualization's sake. And so for analysis, I would look at what kind of Nash equilibriums would exist in this market, and that would be the ideal bids for each of the participants. And so there can be more than one Nash equilibria. It just depends on how the participants decide to bid, sorry. And there are algorithms that can calculate that for you based off a utility function. You could algorithmically iterate to the Nash equilibriums. And so the question is, with this bidding, how can water be added to this analysis? And so one way is to do an effective water cost where, again, the BI parameters incorporates the fuel costs, so natural gas, coal, nuclear, so on and so forth. And so you can embed an effective water cost into that fuel cost and rerun your OPFs and see how the Nash equilibrium change with that kind of implementation. Or you can create a megawatt constraint where the max megawatts available by a generator are constrained by some sort of water limit. I find this one to not be as straightforward because there's more publicly available information relating to the first methodology. And then, again, as I mentioned, study the changes in Nash equilibrium. And so just briefly, I'll go over what cooling types are available and how that affects the water usage. So for once-through cooling, you have a water source, you take in some water. So you'll have a steam turbine. This is a steam turbine example. So you'll run steam through the turbine, but then you need to recycle that steam to bring it back in for the next cycle. And so what you do is you have a river or pond where you bring in cold water to return that steam back into, to condense that steam and return it back to water. And once you condense the water, you can recycle it back, have the combustion again, and you create steam again for the next cycle. And so this withdraws a lot of water. And so withdrawal is basically you take water in from a source and you put it back in that source. And so this, of course, because you just take it straight from the pond and you cool all of the steam with the water you're taking, you withdraw a lot of water to cool all of that steam. Then there's closed loop cooling. This was intended to withdraw less water. What happens is instead of just having a river or pond, you'll have a cooling tower. So this cooling tower will recycle the water it uses. So again, the steam comes into the condenser. The cooling tower will cool the water, again, same as before. But with the cooling tower, what happens is in order to cool the water down for the next condensation cycle, you'll just remove, you'll allow some of the water to evaporate. That'll lower the temperature of the water if you do thermodynamics. And then you just take in a little bit more water to make up for that evaporated water. And so it reduces the withdrawal significantly, but it increases consumption. And consumption is just defined as how much water you lose to evaporation. So it's less withdrawals, but it's more consumption. And so for the effective water cost for these and other technologies, there's a paper by Professor Stilwell looking at the water energy nexus in Illinois. And it looked at, well, what happens if you retrofit the once-through cooling technology with, and you provide generators with recirculating technologies or closed loop, and what does that capital cost look like? And based on that capital cost, she found that there was an effective water cost of about 3 to 6 cents per cubic meter. And so I use that as an estimate and combine that with water withdrawal consumption factors that have been released in other paper reports. And if you take the product, you can get a water fuel cost, an effective fuel cost of water. And so just an example. So this is from the NRO report, where based on the cooling technology, the cooling type, and then the technology and the fuel type, they have a bunch of parameters. And if you combine that with the 3 to 6 cents, then you get an effective water cost for the open loop and closed loop technologies based on the fuel types. And then since I got this data from an Illinois paper, why not use it on an Illinois synthetic case? So this is a case so Professor Overby is doing a lot of research in synthetic networks with some of his students. And so they've been developing purely synthetic networks because the issue with cases like the IEEE test cases is they're not as based in real world load location, generation locations as synthetic cases are. And so they want to create some more practical cases and just have a methodology for where if students want to do research with a certain geographical location, just one button click and you can get a regional grid with some measure of realism. And so all the generators in this case come from publicly available generation data from the Energy Information Administration. So they're actually generators based in actual Illinois, but the rest of the grid is synthetically built around that generation. And so I use that. I've been using that for my work so far. So there's one little caveat. And so previously I said we can bid higher than marginal cost, at marginal cost, or lower than marginal cost. And the thing is, in the 3 utility example, we knew utility A knew utility B and C's cost coefficients. You can't make that assumption. So if you want to go forward, going forward with this, I would like to work with the assumption that as utility A, they really don't know B and C's cost coefficients, but they can ballpark them based on some probability and publicly available data. So what happens to the analysis? Well, there's actually been research on game theory with incomplete, what they call incomplete information. And so instead of doing what they call pure strategies, where I knew which strategy to choose, I chose it with probability 1 because I knew what everybody else looked like in the system, I have to now assume that I don't know for sure what everybody else is doing, but I can probably apply some sort of probabilistic distribution to their behavior, and then from there I'll assign probabilities to my own choices based off of the probabilities and the uncertainties related to their behavior. And so that's called mixed strategy analysis. And so going forward, I'll be making probabilistic models and deciding how utilities will act in a more uncertain environment. And so instead of working with the exact payoff, you use an expected payoff. And so just take the average based off, you weight your payoffs with the probabilities of each strategy, and then you just do an expected payoff. So based on your probability distribution, what do you think you'll get as a payoff? And so from there, that'll be a little bit more work because you have to do Bayes theory and conditional probabilities, but that's currently what I'm trying to get up and running right now. And so future work will be applying mixed strategies to the utility behavior, and from there, developing water scenarios. So some of the EIA, there are a few blanks in the EIA data, unfortunately. So some will say, you know, I'm using coal, but I don't list which technology I'm using, am I open loop, am I closed loop? And so and even if they did provide that data, I could always play around and create scenarios based on what ratio of open loop and closed loop the grid is working with. And so that's currently what I'm working on, and then metrics associated with those behaviors and water vulnerabilities. So acknowledging the Institute ISEE who funds this work. It's a joint project, so there's ECE, there's agricultural, there's civil, there's a little bit of everything. And so that's my presentation.
There's an example for 5, so if you have questions for Desiree,